So now we're going to look at a special development that became popular in the past couple of years, which is a variation of LDPC codes called spatially coupled LDPC codes. So what is the motivation behind spatially coupled LDPC codes? Spatially coupled LDPC codes are a class of provably capacity achieving codes that we obtain just by slightly modifying LDPC codes. So we have block codes. In block codes, what we do is we encode a group of k input bits into a code word x. Then we transmit x over the channel, we receive y, we decode y, and then we proceed with the next block. So it's essentially a block processing of a previous block, then we block process next block, we block process next block, and so on. So it's essentially block processing. Now in spatially coupled codes, we introduce dependencies between the neighboring blocks. So the idea is if one block can be decoded well, the next block cannot be decoded. The one block may help to decode the next block. So they can help each other during the decoding process, and by this they can we can essentially help each other to carry out the decoding and also decode the block that couldn't be decoded initially with the simple code. So what we do is we introduce a new dimension, which is called the spatial dimension. Spatial dimension, which is this, and we call it T, and it describes the block. So we don't use time because the time is reserved for the instance inside the blocks, so it was called a spatial dimension. So every block code or every block is transmitted along a certain spatial dimension. Then we introduce another parameter, which is W, and W is the so-called coupling width. W is the coupling width of our code that we would like to have. So now we look at how we can construct a spatially coupled code, and we're looking at the example of the Hamming code. So what we do is we put some Hamming codes along a spatial dimension. So and here we have 3 Hamming codes along a spatial dimension. So we have the first Hamming code at t equals 1, we have a second Hamming code at t equals 2, and we have a third Hamming code at t equals 3. This is the spatial dimension. And then we introduce another Hamming code at t equals 4, which is what we call a virtual position. So far, there is no coupling between the codes. These are fully independent codes, and this is the case when this coupling factor W, coupling width, is equal to 1. There is no coupling. So now how does the coupling work? So spatial coupling works like this. We consider a chain of L codes. So L is the number of elements along the spatial dimension. And now we're looking at each edge of our tenor graphs. So we touch each edge of our graphs, and we do it in the following way. So we're looking at each edge of the graph at a spatial position t, and we make a random experiment. So we connect it either to a check node of spatial position t, a check node of spatial position t plus 1, or a check node at position t plus w minus 1. And we do a random experiment, and we choose those with a probability of 1 over w. So we throw a dice with w faces, and then we make an experiment, and depending on what the outcome of this random experiment is, we either go to check node of spatial position t, check node of spatial position plus 1, t plus 2, and so on. And we do this such that the degree distributions are preserved. So again, we have some sockets in our check node, and we need to make sure that the number of sockets doesn't change so that we preserve the number of sockets. At the boundary, you will get some issues, left and right boundaries. So what we need to do is we need to install virtual spatial positions, both on the left boundary, but also on the right boundary. And this is just to make sure that the degree distributions at the boundaries are being. So what we do is we fix the bits of the code words at the boundary position, at the virtual positions, to be equal to 0. We don't need to transmit them. We can remove the edges at a later point in time. So let's take a look at an example. So this is our starting position. So we start with our t equal 3, or L is equal to 3 Hamming codes. And we look at the example with W equals 2, coupling width of 2. So we have 3 Hamming codes, and we need W minus 1 virtual positions at the boundaries. So we put these 2 virtual positions on here. You can see one on the far side of the slide. So now we remove all the edges. We keep the sockets of the nodes, but we remove all the edges, and then we fill edge by edge. Remove all the edges, and we start with spatial position t equals 1. Remove all the edges. We start with spatial position t equals 1, and we connect. So we take an edge. We either connect it to the check node at the same spatial position, or we connect it to a check node at spatial position t plus 1. We make a random experiment, and this is what we get. So here we have 2 edges connecting to t. We have 2 edges connecting to t plus 1, 1 edge connecting to t, 1 to t plus 1, 1 to t, 1 to t, and 1 to t plus 1. So that's for the spatial position. Now we see the check nodes here. They don't, so not all the sockets of these check nodes, they are filled, because the check nodes have 4 sockets each. In the Hamming code, see here, we have 4 sockets for each check node. So we cannot fulfill them. So in order to fulfill those, we insert some random connections to variable node of the virtual position. That then looks like this. So insert some connections to variable nodes from the virtual position. So now we continue and we move to spatial position t equals 2. We do the same experiment. So for each edge, we choose a free socket, and then we connect the edge to the sockets. We see some are connected to the same spatial position, and some are connected to the spatial position t plus 1. Then we do the same for t equals 3. And here we also see that we need to connect to some sockets from the virtual position. So this is what happens if we connect to the virtual position. So now what we do is we remove the variable nodes and the edges of the virtual positions, because we assume that they are equal to 0. So we can just remove them. That's what we do, and we end up with this code. So now we have created a new code. The new code has a tenor graph that looks like this. So it has a couple of spatial positions, it has a couple of variable nodes, has a couple of check nodes. We count the number of variable nodes. We have n prime is equal to L times n, 21 code bits. And because of the coupling and the virtual position, we have created 2 new check nodes. So we have 2 new check nodes here at the boundary, and they decrease the rate of the code a little. Remember, if you add check nodes to your code, your rate will decrease. So these extra check nodes essentially decrease the rate of the code. Okay, so now we can introduce the regular ensemble of spatially coupled LDPC codes. So we start with the DV-DC LDPC codes, and what we do is we couple them. So we introduce a new ensemble that is called the DV-DC W and L ensemble. As before, dv is the variable node degree, dc is the check node degree, w is the coupling width, so it depends how many spatial positions we put the edges to, and L denotes the replication factor, so the number of spatial positions that we have. So the check nodes only have regular degree at, let me mark this because it's important. So the check nodes only have a regular degree at spatial positions W to L. In the first W-1 spatial positions, we don't have a regular degree because we had some edges to the virtual position, to the leftmost virtual positions. And these will be removed by the construction. So there we have a lower degree, that is smaller degree. And also the new check nodes that we introduced at the new virtual positions, they have a lower degree. So the check nodes at positions 1 to W-1 have a lower degree, and the extra check nodes, they also have lower degree. You're going to see that this lower degree is very important for the great performance of spatially coupled LDPC. But also we see that the extra check nodes, they lead to a rate loss. So what we have is we have a rate loss, and this rate loss is something that we're going to calculate next. So here's, for completeness, we can also form a parity check matrix of a spatially coupled code, and the parity check matrix looks like this. So we have each spatial position is like one of those columns. We have spatial position 1, spatial position t, spatial position t plus 1, up to spatial position n. Spatial position capital L. And this coupling width W is the number of overlapping submatrices. So we can divide each column into W submatrices, and there is always an overlap of W-1 of those submatrices. W is equal to 1, then this would be just a block diagonal matrix, and this is just a concatenation of independent codes. We also see that here we introduce W-1 extra submatrices, and this is the virtual positions. These are the check nodes that come from the rightmost virtual position. So these are over here. Spatially coupled LDPC code has a very structured parity check matrix. It's kind of like a banded structure. It's like a diagonal band in the parity check matrix. So let's take a look at the rate. So we can actually calculate the rate of a spatially coupled LDPC code. And the rate of a spatially coupled LDPC code is essentially the design rate of the dv/dc LDPC code. This is the regular code minus a correction term. So it's the rate of the underlying LDPC code minus a correction term. This correction term is the one that we're going to calculate next. It's rather simple. It just depends on W and it depends on L and on DC. And again, it's a combinatorial exercise to get to this correction term, and it's just counting. How do we get the rate of a code? Well, we get the rate as 1 minus number of check nodes divided by number of variable nodes. 1 minus m divided by n. And this is just what we can do. We need to count the variable nodes and the average number of check nodes. So the number of check nodes varies because we have this random process of assigning the edges. And it can be that we remove some of those edges because the check node has no connections to it. So by just counting, we can then come up with an expression for the rate. So what we do is we assume that each spatial position has exactly n variable nodes. So we have a total number of L times n variable nodes. Nice. We have the first part of the expression is done. Now we count the number of check nodes. So the check nodes in the spatial positions 1 to L, and our check node in the virtual positions L plus 1 to L plus W minus 1. The check nodes in positions 1 to W minus 1, they potentially have a lower check node degree because some of the edges are connected to the left virtual positions and then are potentially removed. So a check node persists in the code if at least one edge connects to a non-virtual position. So we have a check node and it has one edge that is connected to a non-virtual position, and the edges that are connected to virtual position, they are being removed. If that's the case, then we have a check node that persists in the code. What does it mean if a check node has just one connection? It means this variable node must be equal to 0. That's okay. That's a condition that we have, and we can just count these. So we start by looking at a check node in position t equals 1. So we have a check node in position t equals 1. Now each edge connects with probability 1 over w either to spatial position t, probability 1 over w to spatial position t minus 1, 1 over w with spatial position t minus 2, and so on. So we have spatial variables in spatial position from w plus 2 minus 1 to w minus 1. They are virtual positions, and each edge connects with probability 1 over w to those virtual positions. So now we need to calculate the probability that at least one edge is connected to spatial position t. And this is the probability, this is 1 minus the probability that all the edges connect to the other spatial position, the virtual position. That's probably the easiest way of calculating this. So let's summarize here. Probability that at least one edge connects to t equals 1. It's 1 minus the probability that all the edges connect to the other spatial positions. And the probability to connect to the other spatial positions is w minus 1 over w. So you have w minus 1 virtual positions. There are w positions in total, so it's w minus 1 over w. And there are dc edges, so it's w minus 1 over w power dc. That's 1 minus this guy. So the number of check nodes at spatial positions, the expected number of check nodes is n times dv over dc times this probability. That's C1. Now we move to t equals 2. When t equals 2, the situation is very similar. Edges from t equals 2 can connect to either positions 1, 2, or 1 out of w minus 2 virtual positions with equal probability. So the probability that one edge connects to t equals 1, that at least one edge connects to t equals 1 or t equals 2 is 1 minus w minus 2 over w power dc. Again, we get C2. That's the expected number of check nodes at this spatial position. And then we can generalize this for spatial positions from 1 to w minus 1. That is Ci. Ci is the expected number of check nodes at spatial position I. So we have calculated the expected number of check nodes for the first w minus 1 spatial positions. Now, spatial positions w to L, we have exactly n times dv over dc check nodes, because there the situation is clear. No edges are removed. Now we go to the virtual positions. L plus 1 to L plus w minus 1. We start with L plus w minus 1, so the very last virtual position. Again, the edges connect with probability 1 over w to variable node at spatial position L. 1 over w to variable node at virtual position L plus 1, 1 over w, L plus 2, and so on. Very similar to what we had previously. So the probability that at least one edge connects to position L is 1 minus the probability that all edges connect to the virtual position. So it's 1 minus W minus 1 over W power dc. So C of L plus W minus 1 is, again, number of total check nodes times the expected number, the probability that the check node persists. So it's 1 minus W minus 1 plus dc. Using the very same argument as before, we can say that C of L plus I is given by this expression, so 1 minus I over W power dc times n times dV over dc. Okay, so now we have everything. We can put everything together. So the total number of check nodes, or the total number of expected check nodes, is the sum of all Ci. So it's the first W minus 1 check nodes. Then we have the middle ones, L plus W minus 1. They have a clear expression. And then we have the rightmost number of check nodes from the virtual positions. So we put this guy in front, and then we put both sums, so both expressions that we have. And now we can make a small change of variable here. So here we make a change of variable. In this expression, we say J is equal to W minus I, because we want to get the same expression as here. We say that J is equal to W minus 1. That's this J over here. So we have this expression now. Now we can put these two summations, they are equal. So we can take those together. So then we get the final expression. This expression is C, so it's n times dV over dc, L minus W plus 1 plus 2 times this summation. We can simplify the summation further. So this is summation over 1, W minus 1 times is just W minus 1. Let's do this. So we can express the summation also going from 0 to W, then subtract the remaining terms. That's also what we can do. So we go from 0 to W, and now we need to subtract the cases for I equals 0 and I equals W. These are just 2. This is just minus 2, because in both cases the expression here inside will be equal to 1. Or actually, sorry, in the first case, when this expression, when this guy is equal to 0, the summation will be equal to 1. We have it 2 times, so we need to subtract 2. If we have, in the case for W, this will be 1 to the power dc is 1, 1 minus 1 will be equal 0, so it doesn't have an effect. So we can say that this is L minus W minus 1. So plus 1 minus 2 is minus 1, plus 2 times W plus 1. So here is, and also group this. This is minus W plus 1, plus 2 times W plus 1, remaining 1 W plus 1, minus 2 times this guy here. So then we factor out the rate of the code. So it's 1 minus C over V. And then we just put everything that we have. So n times dV times the simplified expression divided by n times L. First thing, we cancel n. And then we cancel L in the first expression. So this will just be 1 minus dV over dc minus this remaining term divided by L. And of course, dV over dc. It's minus dV over dc, remaining term divided by L. We can actually show that this last expression, or it's very easy to see that this last expression is always positive. So the rate of the spatially coupled code will always be smaller than the rate of the underlying LDPC code. But we also see that if L goes to infinity, so then this term will vanish. L goes to infinity, this term will become 0, and the rate loss will become negligible. This term will then go to 0, and for L going to infinity, the rate of the spatially coupled LDPC code approaches the rate of the underlying LDPC code, parameters dv and dc. So when L is large enough, the rate approaches the rate of the underlying LDPC code, parameters dv and dc. Okay, so we have seen the main construction. Now we will look at density evolution in the next video.